So right, so we fix a differential field. We denote its derivation by this delta, and well, often the constant field C also plays a role. So that's the subfield of K consisting of the elements whose derivative is 0. And yeah, this ring of differential operators, yeah, it consists of all these finite sums, A0 delta to the R plus A1 delta to the R minus 1, etc., where the coefficients are from K. And well, they look a bit like polynomials in delta. And in fact, although this ring is in general non-commutative, there are many analogies with the polynomial ring just in one indeterminate x. And I already mentioned one, the Euclidean division, which has two versions, a left and a right. And you have left ideals are generated by one element and right ideals are generated by one element. Now, of course, you know that a polynomial, a non-zero polynomial over K has only finitely many zeros in K, or in any, or in fact, at most as many as the degree. It has at most as many zeros as a degree of the polynomial, even if you go to extension fields. And there is a nice analogous fact also for linear differential operators. Namely, if you take the kernel of this operator, when you view it as a linear map from K to K, a C-linear map, then so this is a C-linear subspace of K, capital K. It's finite dimensional, and in fact, its dimension is at most the order of the operator. So here, this is just analogous to what I mentioned about polynomials. And again, just like for polynomials, if it really has as many zeros as the degree, then you can factor it into product of degree 1 polynomials, and of course that is a particularly favorable situation. And likewise, if the kernel has exactly dimensioned order, that plays sort of the same role for when you are dealing with linear differential operators. So this suggests that I also say something about factorization, which will indeed play a role. Factorization in K delta. And so, well, first, let A in K, let A be an element of K. Then what are the zeros of delta minus A? Yeah? Then for Y in any differential fields extension field containing K, what does it mean for this, let's say, linear or degree order 1 operator to have Y as a 0? Well, it means Y prime minus AY is 0. Well, let me restrict here Y to be non-zero, otherwise it's not interesting. And that, of course, is the same as saying that A equals Y dagger. Yeah? In other words, A is the logarithmic derivative of Y. So, so it's a bit more complicated than for ordinary polynomials, where a linear polynomial x minus A vanishes at Y is simply equivalent to Y equals A. But here it's Y equals that Y dagger equals A instead. Right. And so therefore, what does it mean for A to be a multiple, a left multiple of delta minus A? well, this means that well, using this fact, one can easily show that this is equivalent to A vanishing for an element in an extension whose such that A is the logarithmic derivative of it. Yeah? A for some y non-zero in an extension in a in some yeah, let me just write L containing K differential field extension with A equals y dagger. Right. Okay. Right. Yeah. Oh, well, the equivalence still requires, how do you prove that? Well, you simply write, you do Euclidean division, right? A can be written as Q times delta minus A plus, well, plus a remainder that has to be of lower order than delta minus A. But the only lower order available is R0 and minus infinity. So let's say plus B, where B is an element of K. And if you now plug in AY is, if you now, yeah, I mean, this direction is obvious. Let me see, yeah, this direction is obvious. So I'm really only looking here at that direction. If you have A, if you write A this way and you have AY 0, then plug it in, this will vanish. And that means that since this also vanishes, that B is 0. And so you get A is indeed of this form. Anyway, that is just a small observation. And of course, we also have the notion of irreducibility. Yeah, we call A delta irreducible. It's like with polynomials. If first of all, the order should be positive. Yeah, if order 0 means simply that A is an element of K itself, or non-zero element of K, and those are simply units in the and we don't want to consider those as irreducible, and it's not the product, and A is different from BD for all BD in K delta of order greater than 0. Yeah, yeah. You might wonder why I write instead of, why don't I write BC? Well, obviously I can't use C because C is the constant field. So I use never C as a name for a linear operator because I've reserved it for the constant field. Okay, and of course, delta minus A is obviously irreducible. Yeah, of course, that you use the fact that the order of a AB is always the sum of the order of AB is the order of A plus the order of B. It's just like degrees. Just behaves like the degree of a polynomial. Okay. Right. Yeah, every A is a product of positive order, is a product of irreducibles. Yeah, that's pretty clear. Every A in K delta positive order is a product of irreducibles Yeah, because you just factor it till you can't factor anymore. and then but it's not unlike in the case of ordinary polynomials. The factorization is not unique, even allowing, you know, multiple, even allowing factors on the left by non-zero elements of capital K. It's not unique. One can. There is a whole theory about to what extent it is unique, but I'm not going to get into that. There are various notions of equivalent factorizations and so on, but yeah. But I want to say what it means for A to split. Yeah. A splits. A splits over K. Well, first of all, I require it to be non-zero, otherwise it's not interesting. And well, yeah, well, in fact, it will follow from what I write next. A is simply a product of order 1 factors. Yeah, AR. Yeah, for A1 up to AR and K, and A not zero. So this, yeah, it's like a polynomial factoring into linear of degree 1 factors. And yeah, okay, let me mention just another fact. So A.
This is not unique either, or not?
Right, it's not unique. No, I mean not at all. Well, yeah. Let me. Okay, if A is not zero and A equals BD, then A splits. Yeah. Okay. I usually say you have to, of course, add this to be precise, but I often, if K is clear from the context, then I won't mention K, but A splits over K if and only if B and D splits. B and D split over K. You actually have to, okay, okay, this direction is fairly easy, although even that requires a little bit of a proof, because when you, if you write B and D in this form, the factor in front of D have to be moved all the way in front, which, I mean, that's a routine thing to do, but still. This direction does require a little bit of work, actually. But okay, I mean, everything I say about these, the basic facts about linear differential, about differential polynomials and linear differential operators are, all that stuff is in chapters 4 and 5 of the book. And when I say the book by Matthias, Joris, and me. And I only mentioned some fairly simple things about from those chapters, but simply the facts that we need most. Yeah, I also have to come back a little bit to the differential polynomials. So what I was saying up till now is about linear differential operators, but coming back, returning to the differential polynomial ring. Yeah. Yeah, so think of, yeah, this is this. So here the things are given by expressions, some, well, AI I0 up to IR, y to the power I0, y prime to the power I1, and the arc derivative of y to the power IR. So these are, yeah, for all R and all, yeah, A, R is 0, 1, 2, etc. So R here is an upper bound for the order of your differential polynomial, and the coefficients are R and K, right? The thing is that there are some useful operations on these differential polynomials, and one of them is called additive conjugation, and another is called multiplicative conjugation. So so P for Py, Ky, and A and K, we have we define two. We have P plus A, Y is, well, P of A plus Y. Yeah, so you just plug in for your indeterminate Y, A plus Y. And of course, that means Y becomes A plus Y, Y prime becomes A prime plus Y prime, and YR becomes the R derivative of A plus YR. And then you have to raise these things also to the corresponding powers. Yeah, these, of course, these coefficients don't change, but oh, yes. And likewise, you have the multiplicative conjugate. Yeah, so this is the, yeah, we call this operation additive conjugation by A, and this is multiplicative conjugation by, so this is the AY. And these are up kind of, and there are all kinds of basic elementary facts about them and how they interact and so on that are used all the time. And that, yeah, well, one thing that is worth mentioning, perhaps the order does not change when you do this. And here, of course, well, of course, for the case A is 0, the order could actually drop, but if A is not 0, then again, the order does not change. And yeah, so for A non-zero, the order doesn't change, and also the degree doesn't change in this for multiplicative conjugates. Yeah, in fact, the degree here doesn't change either. But in fact, it's even true that the homogeneous parts are preserved, right? If P equals the sum of the PDs, of its homogeneous part, then P cross A is the sum of the PD cross A. And PD cross A is the same as P cross AD, yeah, which is, let me write it this way, P cross A D. D being the homogeneous part of P of degree D. So, so multiplicative conjugation is, let's say, commutes with taking homogeneous parts. All these little facts do play a role, and right. Now, but a more intricate kind of conjugation is, which plays a very big role in our work, is compositional conjugation. And in fact, I need to define that carefully, because that is really yeah, maybe I should say a bit more. If you, okay, I mean, typically we try to understand a differential, the behavior of a differential polynomial in the neighborhood of one, or yeah, when you are in an H field, for example, so you have a topology there, evaluation topology, you try to understand how a differential polynomial behaves when you evaluate for elements near one or asymptotic to one or whatever. But of course, when you do this multiplicative conjugation, near one becomes near A. In this way, you can basically, once you understand the behavior of arbitrary differential polynomials near one in some fashion, you can use that knowledge to understand its behavior near A as well by just, well, either the additive or multiplicative conjugation, depending on what kind of problems you are dealing with. So that is one of the roles of these conjugations. You just transform the problem to one where you can study everything near zero or near one. Okay, now compositional conjugation. That is more, yeah. So here I can say that this doesn't seem to be standard material, at least I'm not aware of it as, but okay, but for us it will be essential. And the moral of this whole thing is sort of the same moral as for these conjugation, but it's let phi be a unit now. I mean, a non-zero element of K. And we want to, what we want to do is replace the derivation delta by, yeah, how shall I say that? replacing delta by funny delta. I'll just pronounce it as funny delta, but you see that it's this derivation. Yeah, so yeah, it's a well-known fact that if you multiply a derivation on the left, right? So you, yeah, so delta of applied to an element y is simply phi inverse of y prime, right? Where y prime is simply another notation for ordinary delta applied to y. Yeah, okay, funny delta. If someone knows a better pronunciation, I'd be happy to accept that, but for the moment I'll just call it funny delta. Replacing this by and rewriting an ordinary, rewriting a differential polynomial, py and ky in terms of funny delta, right? So yeah, can drastically simplify things. Can drastically. Yeah. We will see examples of that. Drastically simplify. And it can happen that a differential polynomial, when you rewrite it in terms of this new derivation, becomes much simpler to understand. You kind of unveil it, or if you like. Okay, now here are the details. I mean, this is all pretty vague details. Yeah, so first of all, we have to understand that if we replace the given derivation delta by funny delta, what we are really doing is change the differential field. So k phi superscript phi is by definition the differential fields with the same underlying field as k. Yeah, with the same. So you don't change the underlying field. Underlying field as k, but but with derivation, the distinguished derivation of it is not delta, but funny delta, but with derivation delta instead of delta. Yeah. Okay. And yeah, so maybe a few. Okay, you can easily see. Well, if you take phi as 1, that doesn't change anything. Yeah, so k1 is just k. Yeah, because 1 inverse is 1, and so. But it's kind of like an action of the group of non-zero elements of k, namely if you take k, if you take k phi and you can do it again, right? You can then take a non-zero element again of your underlying field and compositionally conjugate k phi. This is the same as right? That's, I think that is pretty clear. Right. So now the goal is to associate to a differential polynomial over k, a differential polynomial over k phi that behaves in the same way when you evaluate at elements of the underlying fields. So, so we shall associate to any ey and ky a differential polynomial which we write as p phi y, which is now in k phi y. Such that for all y and k, when you evaluate p at y, you get the same as when you evaluate p phi at y. Right now, of course, you have to be aware this is an element of k, of the underlying field of k, right? And this is also an element of the underlying field of k, although k and k phi are different as differential fields, they have the same underlying field, and as elements of the underlying field, they are, that's what this says, they are the same thing. So and actually this will happen not just for all y and k, but for all y in any differential field extension, yeah? Even for all y in L in any differential field extension. Yeah, because yeah, use then of course this will be an element of the underlying field of L, and this will be an element of the underlying field of L superscript phi. But they have but those are the same underlying fields again. Yeah, of course L, if you have this, then also L phi is an extension of K phi, right? So yeah, so if there are any questions about it, ask me now, because I'm right. Of course, this is what we want. I haven't said yet how this is how do we do this? Well, that's what I'm going to do next. Let me see. So far, we are just working purely in the setting of differential fields. No valuation or ordering. Occurs in the story, but that we'll soon get back to that. Okay, so how? So well, in K delta, yeah, if you we set well, okay, here delta is really just a symbol, right? Although when we evaluate, it is evaluated as if it was the derivation of K, but then you can also make sense of this as an element of right now. We now want to view funny delta as an element here for the moment again, and so we can okay, so that means that delta is phi funny delta. Yeah, I'm just putting the okay, and now we are going to see what this means for the powers of delta. So therefore, delta squared equals, we are just making doing the product in here, phi delta is phi funny delta. Now we put these, we have to bring all the scalars, so to say, all the elements of K to the left. So this is phi, and this is phi delta, phi funny delta plus, and now the derivative of phi with respect to funny delta, which is phi inverse phi prime, and then delta. And if you multiply it out, right, this is delta phi. If you multiply it out, you get phi squared delta squared plus and phi prime funny delta. Yeah. So here we have the funny deltas again. Right. And let me do one more, but I'm not going to do it delta cubed. Let me just write down the results. Well, of course, I could multiply phi squared delta squared plus phi prime funny delta squared funny delta multiplied by phi delta again. And if you multiply it all out, you will get phi cubed funny delta cubed plus 3 phi prime delta square, the funny delta square plus, and then phi double delta, yeah. Here we have to keep in mind that phi prime is phi prime, I use phi prime for ordinary, right, and phi double is, etc. So, yeah, so in general, it looks like that. I mean, you can easily come up with the right recursion formulas. Delta to the power r is of the form f r phi funny delta to the power r plus f r minus 1 phi funny delta to the power r minus 1 plus FR1 phi delta funny delta, right? It's, in other words, the sum over I equals 1 to R F R I phi delta to the R, funny delta to the I, where what are these F R I phi, these coefficients, right? So F, where F R I is simply some differential polynomial with rational coefficients. And Q, with rational coefficients, in other, of course, the derivation is trivial on Q. And Q is part of the constant field of K. Right, so these are certain, right? And for example, you can, for example, FRR x is simply x to the power R, which you can see here you have phi as the leading, let's say, the coefficient of the highest power of funny delta. Here you have phi squared, here you have phi cubed, and so in general you have phi to the power R, and FR1 x is simply x, the R minus 1 formal derivative of x, which again is here you see phi prime, here you see phi double, and so in general it will be right. So I mean, and one can come up with simple recursion formulas for these differential polynomials that play a role, and of course this also makes still sense for R is 0. Delta to the power 0 is simply funny delta to the power 0, and both are just 1. Okay, so what is this? Well, this suggests how you, so this suggests, well, let me see. Maybe I should continue on another blackboard because so we now want to translate this information to the case of differential polynomials. I mean, these are identities in the ring of differential operators, K little delta, right? But what it suggests, I hope, it will turn out that this will work, defining this. Recall that what we really want is to define a certain map from the differential polynomial ring over K to the differential polynomial ring over K phi. To be the K algebra morphism sending, well, what should it do if you want to define this as a, and of course we want to make this a K algebra homomorphism. Sums go to sums, products go to products, and the elements of K should go to themselves. And what, so it's completely determined by saying where YR should go. So sending YR to, well, just I equals 1 to R F R I phi y I. Right? I mean, the R derivative, which the R derivative, ordinary derivative, in terms of the new derivative, is this. And so the R derivative of the ordinary R derivative in here should correspond to this thing in here. Okay, and that's how we define this K-algebra homomorphism, and this works. I mean, this works. Oh yeah, and maybe one should y should go to itself. Yeah, y to. Yeah, one might wonder what this means for R is 0. Well, strictly speaking, for R greater than or equal to 1. For R is 0, this sum would be 0, but y goes to y itself, because for ordinary polynomials in y, of course, that's a part of both k of this differential polynomial ring and this differential polynomial ring. So let me say that again. The ordinary polynomials in y form a common subring of both. And then okay, so this works in the following sense. This works. I mean, it's pretty easy to check that p phi y equals py, just like for all y and k. Yeah, for y and k, and actually for y in any differential field extension. Right. Right. So maybe let's. So note this. Yeah. Note. So if you apply y phi equals y, that's what it means to send y to y. What is y prime of phi? Y prime of phi equals, well, phi y prime, y double prime of phi equals what? Now I have to. These things are not always easy to remember. Phi square y double plus phi prime y prime. Yeah, so right, etc. Yeah, and in fact, it's an isomorphism of K-algebra isomorphism, right? It's bijective. Yeah? P phi ky to k phi y is a K-algebra isomorphism. Right, but you have to keep always sharply in mind that when here y prime has a different meaning from, or is evaluated in a different way from y prime here, right? Here y prime, capital Y prime, is simply assigning to every little y its ordinary delta derivative, while here it assigns to every little y its funny derivative. Right. Isomorphism.
Excuse me.
Yes.
Yeah. Are you assuming that phi belongs to k, isn't it?
Yes.
Or
A non-zero element of k.
yeah. because well, what is k superscript phi? Because if phi belongs to k, maybe it's the same field of constants.
Yeah, the field of
No
constants.
constants. Sorry, the same k. I mean, it's
Well, it's the same. Well, k and k phi have the same underlying field, but they are different as differential field. They have a one has derivation delta and the other has derivation funny delta.
Okay. Yeah, it's a notation just for the sorry, yeah, it's only for the derivation, which is different. Okay.
Yeah, right.
Yeah,
right.
okay, yeah.
Yes.
So this preserves irreducibility.
Which map are you talking about now?
The multiplicative
Oh, well, okay. Well, yes, it's a K-algebra isomorphism. If you want to talk about irreducible differential polynomials, which we didn't talk about, but it's true that it preserves that in both directions. But the notion of an irreducible differential polynomial does not play a big role. Well, actually it does, but we haven't. But we are mainly concerned with irreducibility of differential operators. It's a different story. Right. Yeah, okay, so where am I? Ah, yeah, okay. Aha, yeah, so this also is true on the level of differential polynomials. Yeah, it's K-algebra isomorphism, and if you first compositionally conjugate with phi, and then with theta, which is another non-zero element of K, then that's the same as this. In other words, if you can think of this as an action of the multiplicative group of K on the ring of differential. Well, on the underlying ring of differential polynomials, not on the differential ring of differential polynomials. Right. Okay. And another, yeah, so this has very good properties, this compositional conjugation operation. But maybe I should make some more space. Yeah, so let me mention a few more properties of this operation. P phi has same order and degree as P. It also preserves homogeneous parts, also preserves, it preserves a lot, also preserves homogeneous parts. If you take PD, the homogeneous part of degree D of P, and then compositionally conjugate, that's the same as taking the degree, the homogeneous part of degree D of this one. Also commutes with additive and multiplicative conjugation, commutes with additive and multiplicative conjugation. P plus A, if you compositional conjugate with phi. This is the same as P phi plus A, and P cross A phi equals P phi plus A. Right, and so usually when we write, when we talk about, for example, this, we simply omit the parentheses at all because there is really no ambiguity, right? We simply write this, and you can interpret this in two ways, but it gives you the same thing. And likewise here, we simply write this as this way, P plus A. Again, the ambiguity is harmless because you get, no matter where you put the parentheses, you get the same thing. And okay, I mean, these are all formalities that are fairly easy to establish, but although sometimes you do actually have to do a little bit of work. Okay, so now I can get to the setting where we have H fields. Yeah, okay. So now I begin a new, and that will enable us to define Newtonianity as eventual behavior. So this is all background to defining what we mean when we say that an H field is Newtonian. So now K is more than just a differential field, it's an H field. Well, and with asymptotic integration. Well, last time when I talked about H fields, I introduced some extra property at the end, which implies that it has small derivation, but yeah. So for our purpose, an H field, let me redefine it. Let me define it again, i.e., an ordered differential field such that H1, if f is bigger than all constants, then it's, yeah, f is bigger than all constants, then f. So this is and well, if you take the convex hull of the constants, O, it's C plus little o, yeah, where this O is by definition all the things that are bounded by less than or equal to C for some C and C for some positive element in the constants. And little o, what was little o? Little o, so this is a convex subring of capital K, and it's a valuation ring, and so you get the corresponding asymptotic relations. And little o is the infinitesimals, so f, it's the maximal ideal of big O, f less than C for all, less than or equal to C for all positive, for all C and C. Right, and another way to think about this is that, or the consequence of that is that C is a field of representatives for the residue field, right? So since we now have a valuation on capital K corresponding to this valuation ring, if you mod out by the maximal ideal, you basically get C. So here we have the interesting situation that a constant field and the residue field are basically the same, and that will be that is plays a big role. Oh, now K is an H field, so I now define. But I'm going to restrict my attention to those that have. This is the official definition of an H field, but again, just for convenience, I'm going to assume also that the derivation is small. So F. Right. Strictly dominated by 1 is the same as saying it's in the in this little o.
Là-haut,
Yes.
Jean-Philippe Rollin, if you start with a field with a small derivation, is the Fanny delta also small, or does it depend on field?
That's actually what I'm going to
sorry.
discuss, because that is exactly the kind of restriction I'm going to impose on little phi. That, yeah.
Okay. Thank you.
Yeah. Anyway, right. So this means F in little o implies F prime in little o, or in terms of the asymptotic relations associated to the evaluation range, it means this. Yeah, and we think of little o as the infinitesimals. Right, and big O as the bounded elements, if you like. Okay, so I'm going to impose this as an extra axiom, although it's not strictly speaking the official part of the axiom for an H field, but I don't want to. So yeah, I'm next going to also assume that that K has asymptotic integration. Yeah, K be an H field with asymptotic integration. Oh, I should asymptotic. I should. I forgot that I have to. It means that every element is, well, so to say, close to an end to a derivative. Every element is, but the technical definition is that the asymptotic couple, right? I mean, when we say it's really a property of its asymptotic couple, namely that in the asymptotic couple, all the elements are derivatives of, so to say. So let me introduce this asymptotic couple now explicitly. Gamma psi, the asymptotic couple. And you have to have in mind the usual picture. Yeah, this is, I mean, whenever I think about H fields or whatever, similar things, this is the picture I have in mind, gamma dagger, gamma prime. And so asymptotic couple and asymptotic integration means that every element is of the form in gamma is of the form gamma prime for some gamma. Of course, here these things are not it's not defined for gamma is 0, but every element is of the form gamma prime for some non-zero gamma. And that was one of the three possibilities for you have this trichotomy that either having a gap or being grounded or having asymptotic integration. Right. Now, what happens for phi in K, or phi in, now I'm actually going to, because I'm talking about H fields, it is better to restrict my attention to positive elements of phi, little phi, because then for phi in K, it's asymptotic couple. I see now in my notes, I did not impose H3. Forget about H3 for the moment. It's not part of the official definition of an H field anyway. So drop that, because I want to say the asymptotic, what happens to the asymptotic couple if you conjugate, compositionally conjugate? Well, there is a vertical shift for the asymptotic couple. Yeah, for phi, K phi is still an H field. That's why I want to drop H3, because it wouldn't be true if I impose that. Comma with asymptotic couple. What happens to, it's the same, of course, the valuation doesn't change. I'm only changing the derivation. It's little psi now minus the valuation of phi. Yeah, right. So it's the psi function, or the dagger function, if you like, but you subtract always the valuation of phi. So what you do is, if you, I mean, the new asymptotic couple, the psi function might be shifted like that. Right, and of course the derivative function is shifted likewise. So it's a vertical up or down depending on phi, and it might not have. You can shift to any place you like. In other words, in this picture, in the picture that I originally drew, you have asymptotic integration because the derivatives for gamma positive, gamma prime is even more positive. But once you shift down, you might not have this anymore. But right. Now, here is the thing. K phi has small derivation. Yeah, that means, yeah, maybe I should explicitly say H3 is called the property of having a small derivation. It's not part of the definition of H field, unlike what I suggested earlier. But this happens if and only if, well, the valuation of phi is less than capital, the psi set. Right? This is the set of all values of psi, gamma dagger, gamma. Right? It's in the original picture. It is everything below this black hole, if you like. And so whenever the valuation of phi is below this, then right. That is of course very easy to check from this. Yes, right. Okay, so now I'm actually going to small derivation is yeah, it's very useful, and so we are actually going to always restrict phi to have this property, and such phi we call active in K. This happens, and so right, and we are going to, so active means simply that the valuation of phi is this of course doesn't really make sense, less than psi. What I mean is that it's an element of the downward closure of psi. Yeah, okay. What I just said is correct, of course. Psi is the set of all daggers by definition, gamma not 0. But Psi, the downward closure of Psi is all the things that are less than or equal to something in the Psi set. This is called the Psi set.
Is it the same as saying that it's less than the supremum?
There will not be a supremum of Psi. And it's a good point that you raise here. Psi will have a supremum. Well, Psi can have a maximum, which means grounded. It will have a supremum, which is not a maximum, even only if you have a gap. And that supremum will then be the gap. But if you have asymptotic integration, there is no supremum. That's one of those things I should have mentioned, but yes. Right. Okay, now the important phenomenon that I want to discuss is that for X, yeah, so below we restrict, yeah, so yeah, so okay, I hope we restrict phi to be active, phi positive, and evaluation of phi is less than or equal to something in the capital Psi set. Right, and now we can discuss a remarkable, well, in a way it's, with hindsight it's not that remarkable, but it is a very useful phenomenon. Is
Sorry, Lau, do
yes,
active elements always exist in a
Excuse
H
me?
field? Do active elements always exist?
oh yeah. Well, everything, I mean, since we are assuming asymptotic integration, that means in particular that there are, well, anything that is a dagger,
Right.
asymptotic integration in particular implies that gamma
Okay.
is not trivial. Then there are many elements that are daggers. And
Yes.
then anything like that whose valuation is of this form is of course automatically active, right? If phi
Okay. Okay.
is actually in the Psi set, it's yeah.
Okay.
Yeah.
Thank you.
Okay. Yes. Yeah. So now I want to make the following.
If K has a small derivation to begin with,
Yes.
then Phi equals 1 should work, right?
Yeah. Yes. Right. If K already has a small derivation, which of course is always the case when you are dealing with a Hardy field, for example. Yeah.
This
Phi is.
function only if 0 is existing.
For asymptotic integration, well, 0 is in the downward closure of Psi. It doesn't have to be.
I'm just looking at this statement that K has small derivation even only if the value is existing.
In the downward closure of Psi, yes.
In the down closure.
Right. Be less than or equal to something in the Psi set. But of course, if it's in the Psi set itself, then it's active. Now, I want to discuss now the important phenomenon, which for us, I mean, again, it's important to assume here asymptotic integration. So let P be a differential polynomial. Yeah, let me, okay. non-zero to avoid certain trivialities. And as the valuation of phi increases, in the downward closure of capital Psi, this increases. Let me see. What do I want to say? Various quantities associated to P, to quantities associated to P phi. Yeah, so now I'm taking active elements of capital K, right? And I let the valuation of phi increase as much as possible. You make it cofinal, go cofinal in the downward closure of the Psi set. Becomes stabilize, associated stabilize, i.e. become constants, eventually become constants, eventually. And eventually means for some active phi zero, whenever the valuation of phi is still bigger, or greater than equal to the valuation of phi zero, then the quantity that is associated to P phi doesn't change anymore. Right? So eventually meaning for sufficiently high valuation of phi within the downward closure of capital Psi always. Right. So one such quantity, yeah, and that's the crucial one to define Newtonianity. One such quantity is the so-called dominant degree, D-dec. The dominant degree. I'm going to define that dominant degree of P. Now, of course, I'm going to define it for P itself, because then the same definition will apply to P phi. So the dominant degree is simply okay. How is this dominant degree defined? It's yeah, okay. We have the natural differential ring morphism. Oh yeah. Oh, yeah. Assume for now that we are already in the case of a small derivation. I mean, eventually K phi, K superscript phi will have small derivation anyway, right? Or in fact, not just eventually, for all active phi, K hat phi will have small derivation. So assume for now that we are already in that case. So assume K has already small derivation, which you can always reach in any case by compositionally conjugating with any active phi. Or if you are in a Hardy field, it's already the case. Then you can then you have the natural ring homomorphism. Okay. Then O, I forgot to say that, but then O is a differential subring. Differential subring. Well, that's actually obvious now I think about it. Differential subring of K, right? Because big O is every element in big O is a constant plus an infinitesimal, and if you take the derivative of such a thing, well, the constant has derivative 0 and infinitesimal has derivative again infinitesimal. So so you have the natural differential ring homomorphism. Oh, I forgot to, yeah, okay. Of course, this is the subring of ky. And here we go to C y, which is also a subring of ky. Yeah, we can also form the differential polynomials just with the, where all the coefficients happen to be constants. And what is the kernel? With kernel, well, with kernel little o of, yeah, okay, this isn't really defined because little o is not a differential subring, it's just a differential ideal. It doesn't contain one, but nevertheless, I think you know what I mean. It's just all the elements here whose coefficients are infinitesimal, right? All the differential polynomials with bounded coefficients whose coefficients happen to be actually infinitesimal. Right, and so right, so for P, so okay, now for P in ky non-zero, we take an element of k, which that P equals AQ. Yeah, you factor out A from such that the resulting differential polynomial is in OY, but not in the kernel, yeah, such that Q in OY, but Q not in the kernel, right? I mean, if you look at P, then there will be a coefficient of smallest possible valuation, and you take that as A. Yeah, so you take a coefficient of P with the smallest possible valuation, take that as your A, you factor it out, and the resulting differential polynomial will then be have all its coefficients in O, but since you divide it out by one of the coefficients, there still is a coefficient equal to 1, so it's not, so Q will not be in this kernel, and so, and then yeah, what does this mean? Yeah, so P, in other words, P will be A times, and then you can replace Q by its image here, and so A is P equals A times, well, let's call that dP, sort of the dominant part, plus something, plus terms, infinitesimal terms. Infinitesimal terms. dP is now the image, so to say. Yeah, dP is the image of Q in Cy. So it's a differential polynomial which have constant coefficients. Right, and so now the dominant degree of P is simply the degree of this one. So dominant degree P is the degree, the total degree of this differential polynomial. Yeah, and actually this differential polynomial is often called the dominant part of P. Of course, it's only this dP here is only determined up to multiplication by a non-zero constant. It's not uniquely determined, but of course that doesn't make any difference for the degree. Right. Okay. So that is the dominant degree. And I'm saying, what did I say? And of course, this can be done also for when you go to when you compositionally conjugate with phi, you are in the situation where your k superscript phi has a small derivation, so you can do all that. The valuation ring actually doesn't change. Of course, the differential polynomial ring does, because will then be in here instead of here. C doesn't change either. Of course, this will then be viewed as an element of. So, yeah, if you compositionally conjugate, then you have to put phis everywhere, and so the meaning of this, in some sense, depends on phi, but as its underlying ring doesn't change at all. Yeah, all these things have the same underlying ring, although with a different derivation. Okay, and that is okay. So this is what I'm saying here. This dominant degree. If you take the valuation of phi high enough with these restrictions, then it doesn't change at all. Okay, and this now allows me to define what we mean by the Newton, the Newton degree of, So this allows me to define the Newton degree of P as the eventual value of this dominant degree. Right. So the Newton degree of P is eventual value of the dominant degree of P phi. Yeah? And it's a theorem, or well, a proposition. It takes a little bit of work to prove that this exists. The eventual value of the, when you let the valuation of phi increase as much as possible, eventually it will stabilize. Yeah, so that's called the Newton degree of P. So when I use the word eventual, it's always with respect to when you let the valuation of phi become big enough. Inside, still with this restriction, of course, that phi is active. Okay, of course, the Newton degree of 0 is defined to be 0, is defined to be minus infinity. Okay. Example, yes. I think all this will perhaps become more concrete if I show you a very explicit example. P equals, let's say we have a differential polynomial which is b y squared plus y prime, where b is some coefficient from k, which for the moment I don't specify. And so then what is then p phi? What is p phi y? Well, y doesn't change, so it's still by squared. But y prime changes. I know, my example had this. It's a little bit more interesting to take the second derivative here. So y double becomes phi square y double plus phi prime y prime, where the derivative is now taken, phi prime is simply the ordinary delta derivative of phi. And okay, so you have to look at what is the dominating term here. So here you have coefficient b, here you have coefficient phi squared, and here you have coefficient phi prime. So which is going to dominate? Because that determines how you form the dominant part. Right. So now, if you think about it, eventually, let's just compare these for the moment, phi squared and phi prime. Which is going to be the dominant one eventually? Eventually, we have phi squared much smaller than phi prime. Yeah, because dividing by phi both sides, phi will eventually, because dividing by phi, if phi is active and the valuation of phi gets big enough, then you eventually will have this. That's just a fact that that's not hard to show. So in other words, this is dominates, this is bigger eventually than that. But now, of course, that still has to be compared with B. So, but you have only two possibilities. Either B will, the valuation of B will eventually, yeah, so if B eventually if B is eventually strictly smaller, and this can happen, then then this will really be the dominant coefficient, right? And so that means that the dominant part of P is just you divide out by phi prime and you get y prime. Oh, sorry, dp phi equals phi y is y prime. And so the dominant degree, the Newton degree, right, which is the eventual degree of this, will be 1. But it also can happen that B is eventually dominating phi prime. Yeah? And it's again a fact that has to be proved, but it's true that eventually either this will happen or that will happen. Eventually, then dp phi. Okay, in that case, this will be the dominating coefficient, and so then dp phi equals. So then you divide out that, and you get y squared. So the Newton degree of P equals 2. Right. So it depends on where this coefficient B is located, what the Newton degree is. Okay. Yeah. So this. Yeah. So it's not actually not only the dominant degree that that eventually stabilizes, eventually becomes constant, but even the dominant part, this dp also becomes eventually constant. Well, there's a small technical issue here that this dominant part is only defined up to multiplication by a non-zero constant, but let's disregard this for the moment. So it turns out that this And that is called the Newton polynomial associated to. So, yeah, non-trivial fact, but it's not too hard to prove. The dominant part of PV also eventually stabilizes, becomes constant. Again, there is this minor issue about it's only determined up to a constant factor, and is called NP. NP, the Newton polynomial. But you can very easily, that you can see, of course, very clearly in this example. Here the Newton polynomial is y prime, here the Newton polynomial is y squared. The Newton polynomial of P.
Is it how you, sorry, Lau?
Yes.
Yes, is it how you prove that the Newton degree exists via the stabilization of a Newton polynomial?
Yeah, in some sense it's yes, it's really the Newton, it's really the dominant part here that you show stabilizes, and then of course you have automatically.
Okay.
So this is in some sense the better result, right? Because
Yeah.
then you get, and that's what you really prove, right?
Okay, thank you.
And this Newton polynomial, you can imagine that it is a very useful thing, because it basically your differential polynomial capital P that you're interested in, once you compositionally conjugate it enough, it will basically be just an element of K, non-zero element of K, times this Newton polynomial plus small terms, infinitesimal compared to n sub P. And so that enables you to study the behavior of P near, well, for elements that are asymptotic to 1. Okay, and now let me see what, yeah, so NP, yeah, and it's a very special kind of differential polynomial since it has constant coefficients, and NP very useful. Yes, yes, go ahead. To describe
The derivation in this is it the funny delta or?
well, the funny delta changes with phi.
Yeah.
Yes, so for the moment, you should simply consider this as a ring, and not as a differential. Well, yeah, actually, in a way, if you think about what this means, yeah, so it's of course in K phi y, but in fact, even as a differential ring, it doesn't change because you see all the funny deltas, when you restrict it to C, it's still trivial. So in other words, yeah, you can actually consider this as a differential polynomial over C because all the funny deltas are still trivial on C. So that's why, yes, right. NP very useful to describe behavior of Py or Y asymptotic to 1. Right, and if you then also multiplicatively conjugate by arbitrary elements, you can describe the behavior of P near any elements that you are interested in. Why does it squeak? Let's see if this one. now, oh yeah, I still have. So now I can say what we mean by K to be Newtonian. Yeah. K Newtonian every, so that's the definition, every P in KY with, yeah, of course, the Newton degree of, yeah, strictly speaking, I did define this only for non-zero P, but of course for zero, for if P is zero, you define this to be zero, right? And the Newton degree will be minus infinity. But every P with Newton degree 1, yeah, and these are also called quasi-linear, has a zero, in O. Yeah? i.e. Py equals 0 for some y, for some bounded y. So this is a kind of super version of Henselianity, right? For if you are familiar with some valuation theory of ordinary valued fields, then Henselianity also means that certain kinds of differential of ordinary polynomials have zeros. It turns out that this is somehow the right notion of analog, so to say, of Henselianity in our context. Well, there are other notions of differential Henselianity that are connected to this, but I'm not going to get into that. Okay, and so this is the key concept that we are going to discuss next week more, but let me see. Let me make a theorem. This is a very important. Let me now make the following statement. K is omega free is equivalent to that the Newton polynomial is of a very special form for all P and KY. Its Newton polynomial is an ordinary polynomial times a power of y prime. See how remarkable this says the Newton polynomial does not involve higher derivatives. The only derivative that it involves is y prime. There is no y double, or and it appears in a very special form, namely it's an ordinary polynomial in y times the power of y prime. So that is one of the, one should also say that a lot of this is inspired by the work, the previous work by Joris van der Hoeven, who wrote the Springer lecture notes, where he studied in very great detail a certain variant of the differential field of Transseries, namely differential field of grid-based Transseries, and the methods are rather special to this situation, and so a lot of our work was simply making generalizing for this very special H field to well, arbitrary H fields. And in fact, we do it in a more general. All these things make sense in a more general setting also, not just H fields. But anyway, but a lot of, for example, this fact was this fact that all the Newton polynomials are of this form was already proved in that Springer lecture notes. But the methods that he uses have to be modified considerably to give you this fact. But this is a non-trivial. It takes certainly something like 50 pages to prove this in detail. Okay, now I have to stop, I think. Yeah, so now, so next week I can say more about Newtonian and the relation to omega freeness, and yeah, maybe I should. We don't actually know whether Newtonian implies omega free. Yeah, question mark. In principle, they have been defined independently of each other, and we don't know whether Newtonian implies omega free. Certainly, omega free does not imply Newtonian, but it could be that Newtonian implies omega free. We don't know. It does imply Newtonian does imply lambda. Well, do we actually know that? I think it does imply lambda free, if I'm not if I remember correctly. But I'm not even betting on that for the moment. No, even that I'm not sure about. Anyway, this. But it turns out that the two properties together are really where the power, where all the power is. So, but we'll say more about this next week, and then try to give a sketch of one of the main results in our forthcoming notes on Hardy fields. So you have to relate this now to Hardy fields also. Right. So is there an exercise session after this? Is there?
Yes, there is a question session.
So when shall we start? At 10 o'clock? Or I mean at 11? Or?
Whenever you're ready, Lau, or just
Oh, okay.
give people the time to go to the bathroom and then we can start.
Yeah, so let's start at 11 then. Or 5 past 11.
Okay.
Because 5 past 11, let's have this. I can say a few things also that I forgot to say earlier, but which should